Okay, so hello everybody. Welcome to today's AI for EO lab talk. Today we have the honor to have Professor Jonathan Bamber with us. Before we start, I would like to give a brief intro to Jonathan, although I believe most of or everybody of this round familiar with Jonathan, but since this is a recorded talk just for the general public. Jonathan is a professor of Earth observation and glaciology at the University of Bristol. And there currently he's the director of the Bristol Glaciology Center. And he's also a guest professor in our AI for EO Future Lab. He's when it comes to data science, he's currently a fellow of the UK Data Science Center, the Alan Turing Institute. And from the training, he has a degree in physics from Bristol and a PhD in glaciology, remote sensing from Cambridge. He has more than 35 years experience in the analysis of airborne satellite data sets, specializing in combining this data with models of the Earth system. And he's an expert on ice sheets covering Antarctica and Greenland and the contribution to sea level. So this is also the background when Jonathan and our future lab get into contact. So quantification of uncertainty is a very important topic in the future lab. This is also particularly important for the use case where Jonathan is working on. So we thought it's a good actually opportunity to combine the expertise from the both sides and try to make some progress in quantification of uncertainty in all this kind of modeling process of sea level and glaciology. And yeah, so there's a lot of achievement from Jonathan, but what I would like to highlight is that he was the former president of EGU, is a fellow of AGU, and it's a very, let's say, highly cited scientist in the community. So today we will have basically him talk about the challenges of predicting future sea level rise and its potential consequences for society. So Jonathan, the floor is yours.
Oh yeah, thanks very much for the introduction. Actually, you've just I can delete my first two slides because you've covered all of that now. But this talk is going to be a little bit different from perhaps some of the others. I'm going to keep it very high level and just try and introduce some of the challenges and problems that I've been working on over the last, let's say, roughly last decade. It's quite difficult for me to sort of summarize what I do because I actually have worked on a kind of lot of different problems over the last few decades. And I'm going to mainly, in terms of results and the approach, I'm mainly going to focus on some work we've been doing as part of ERC funded project, which is pretty much coming to its end. It's got about 8 months left of funding, but I'm going to talk about the ERC project, which is called Global Mass, because I think it epitomizes many of the approaches and kind of methods that I've been using over the last few years and have developed in my research. So let's see. Okay. All right. I can probably skip all this because Zhang's already mentioned it. I've worked with lots of different types of sensors over the years. Mainly, I think I'm probably best known for my work with satellite and airborne laser and radar altimetry, but also done work with SAR interferometry, mainly for ice surface velocities, but also a little bit for vertical land movement, and worked with infrared and visible radiometers and visible imagery to some extent as well. I'm gonna, yeah, so me, how do you describe yourself? Well, I'm a glaciologist, Earth observation expert, climate scientist, human being, all of those things really. Yeah. And just for fun, I've never done this before. I thought I'd produce a word cloud so this is from just the titles of all the papers I've ever published. And I don't know, I just thought it'd be a fun thing to do. And it's sort of reassuring to see that some of the key things that I think that, I've done a lot of work on, I've done a lot of work on digital elevation models of the ice sheets, but also global land topography. Data is quite prominent there, which is good to know. Satellites, radar, modeling sea level altimetry. So it kind of does capture the kinds of things that I've been working on over the last decades. Very briefly outline what I'm going to talk about today, if I have time to cover all these things. As I said at the beginning, I could whistle on for hours on some of these topics, so I'll try and keep it kind of brief and just give you the key messages, if you like. But I'm not sure. I guess many of you are from a data sciences background, so I thought I'd just run through some of the sort of background to what influences sea level, why it's important, and some of the issues around projecting and predicting what it's going to do in the future. And then I'm actually not going to show too many results from the ERC project itself because, well, for various reasons. I mean, we're still working on them, and actually some of the problems we're tackling we haven't really solved just yet, even though we're sort of towards the end of the project. So yeah, that was briefly what I aim to cover, and just start with the components of what's called the sea level budget, what contributes to sea level rise. And the fascinating, interesting, and exciting, to me at least, thing about sea level rise is that it integrates so many different Earth surface and climate processes. And so if you're able to actually partition the integral of sea level rise to those component parts, you can learn a lot about the response of the climate system to external forcing, to human-induced, say, global warming, for example. And this figure illustrates the various different components. So you've got, well, let's start with the hydrological cycle. So that's basically mainly precip over land. So that influences sea level, not at the global mean by a large amount, but regionally, locally, sea level is very heavily influenced by changes in precip, but also human-induced impacts like irrigation, dams, and reservoir impoundment, things like that. And so we've got groundwater here. Then there are processes in the ocean itself. There are changes in ocean circulation, which again, the integral is 0, but you see big regional variations in sea surface height due to changes in circulation and heat content locally in the ocean. Obviously, important component is the thermal capacity of or changes in temperature of the oceans. That's called thermal expansion, or the thermosteric component. As the ocean warms up, with climate change, then obviously it expands, and you see a global signal, but you also see big regional variations in the thermosteric component. And then, of course, you've got melting of glaciers and ice caps, and the 2 ice sheets that cover Antarctica and Greenland. You've also got a component due to changes in what's called vertical land motion, or VLM. As you load the oceans with more water, the ocean basins actually depress. You have an elastic response of the bedrock underneath, and you've got vertical land motion due to other processes on non-ocean covered regions, which also affects relative sea level. So you may have no change in absolute sea level. In other words, the volume of water may change, but you may see a change in sea surface height at the coast because of vertical land motion, or VLM. And that's a particularly sort of interesting challenge in geodesy, which I'm going to say a little bit more about in a few slides. Just a few numbers. I don't want to bombard you with lots and lots of numbers, but the headline figure is in red here. So and that figure of more than it's about 630 million people. That's based on today's geographic distribution of global population. Of course, that may change in the future. In fact, it's likely to go up in the future. So that's about 1/10 of the population of the planet. And a sea level rise of 2 meters by 2100 is a plausible value. It's not the most likely, it's not the median estimate, it's around about the 95th percentile value, but it is a plausible, a credible sea level rise that we might experience by 2100. And 600 million people, you know, that's I think the consequences of displacing that number of people are kind of unimaginable for civil order and, you know, breakdown of society in general. Just to put that number in context, during the Syrian refugee crisis from about 2010 to 17, that displaced 4 million people. And we're all very aware of the sort of, you know, the political fallout from the migration of those people during a relatively short period. And only half of those actually try to enter Europe. And we're talking about displacing something like 150 times that number of people potentially by the end of the century. So that's why it matters. Actually, just an interesting aside, this value of 600 million people, that's a very recent estimate. Prior to that, it was 4 times smaller, and it was revised upwards by a factor of 4 because of a very recent paper published, I think, just about a year ago now, where they revised the coastal topography, and they found that global DEMs were biased high in coastal areas by about 2 meters on average because of built structures and also vegetation. So, and that was a very newsworthy finding. The biggest potential future contributions to sea level rise obviously come from the ice sheets, and these are the headline numbers. So the West Antarctic ice sheet is the bit on the left. I'll show a plot of that in a minute. That has, SLE stands for sea level equivalent. So that has a potential sea level equivalent of 5 meters captured in it. The Greenland ice sheet is 7.4, and by far the largest ice mass on the planet, East Antarctica, has the potential to raise global sea level by about 53 meters. So it's sort of roughly 10 times bigger than any other ice mass on the planet. And so those are the ice sheets covering Antarctica and Greenland. If you took all the other glaciers and ice caps around the world, which generally speaking are sort of categorized separately because they have a different response time, they would contribute about 40 centimeters sea level rise. So in terms of their sea level contribution there, it's sort of at least an order of magnitude smaller than the other ice masses. And this is just a bit of geography, if you like, just to kind of put these ice masses in context. So this is actually, it's a digital elevation model I produced quite a few years ago from a combination of satellite altimetry data sets. And this plot just shows the ice sheets and the Alps to scale. So that's Antarctica. It's a big ice mass. It's about 1.5 times the area of Australia. It's larger than the conterminous USA. And the ice in parts of Antarctica is up to 5 kilometers thick. So, you know, it's a seriously big piece of ice. That's Greenland scale. That's also a DEM that we produced from altimetry and stereophotogrammetry. There's the Alps. Now, I'm not saying glaciers and ice caps aren't important. They're important for different reasons. They're a very, very important water resource, particularly in the Himalaya, Hindu Kush, and Indian subcontinent. You know, there's a figure, it's not quite accurate, but, you know, the glaciers in what are called the Asian water towers provide water to, well, the figure that's often quoted is 2 billion people. That's a bit misleading, but it's less than that, but it's still a very large number of people. It's probably something like half that number, maybe up to 1 billion people rely on meltwater from glaciers in the Hindu Himalayas and Hindu Kush. That's the UK scale. So, yeah. And the difficulty in predicting what sea level rise will do in the future primarily, almost entirely relates to what the ice sheets covering Greenland and Antarctica are going to do in the future. Thermal expansion of the oceans is pretty well understood as as you change the thermal capacity of the oceans, or not the capacity, but the amount of energy that's absorbed, then we understand how the oceans will respond to that relatively well. There are some issues around mixing rates and how long it takes for the heat to reach the deep oceans, but by and large, the uncertainties are relatively small. The largest uncertainties and the largest potential contributions come from Greenland and Antarctica. And one of the factors that makes it very, very difficult to predict what the ice sheets are going to do is that they all three ice sheets contain instabilities, what are sometimes called tipping points in them. And the most worrying and the most well understood currently is something called the marine ice sheet instability. And it's illustrated with this cross section across West Antarctica here. And this is a real plot of surface elevations and bedrock topography across West Antarctica. And the blue here represents the ocean. So what you can see is that the ice in sort of, I don't know, like light brown, I don't know what yellow, whatever color you call that. The ice there is resting on bedrock that's below sea level. In fact, in some places, it's up to 2.5 kilometers below sea level. That's what's called a marine ice sheet, because much of it is resting on bedrock below sea level. The other factor that's required for this marine ice sheet instability is what's called a retrograde slope. That's where the bedrock gets deeper as you go inland, which you can see is the case for this part of West Antarctica here. In that configuration, with that particular kind of geometry, this point here where the ice first comes into contact with the ocean and detaches from the bedrock, that's called the grounding line. This point is unstable. And so you only need to perturb it a little bit by, for example, changing ocean temperatures, which results in melting at the grounding line. And you get effectively a runaway effect where the grounding line migrates rapidly inland and you lose almost all of the ice sheet. And we know from theory that this instability exists. Some recent observations from satellite altimetry suggest that it may even have initiated in parts of West Antarctica. But it's very hard to know where the threshold lies in parameter space. In other words, what kind of temperature anomaly or change in ocean temperatures or change in ocean circulation will trigger this instability? Well, that's a very difficult question to answer, and it makes it extremely hard to know when we might pass the tipping point, and also critically what the rate of mass loss will be over time. Just a kind of quick interlude on the glacial origins of vertical land motion, which is something called glacial isostatic adjustment, which is a fascinating problem in geodesy. If you stick a lump of ice on the lithosphere, it depresses it. The lithosphere is elastic and the mantle underneath is viscous. And so you get a viscoelastic response. And this depresses the lithosphere, and the ratio is roughly the ratio between the densities of ice and the density of rock, which is about a factor 4. So if you have 5 kilometers of ice sitting on bedrock, you're going to depress that bedrock by about 1.25 kilometers, about 1,200 meters. So that's a big signal. When you remove the ice, you get a crustal rebound, which is called glacial isostatic adjustment. And that response is viscous, so it's quite slow. But when you load the surface with, I don't know, water or ice, you also get an instantaneous response, which is elastic, which is much smaller. And we are seeing glacial isostatic adjustment over, well, in particular over North America, because of the loss of the largest ice sheet during last glacial maximum, which is called the Laurentide ice sheet. This is a reconstruction of the Laurentide at what's called LGM, which was about 22,000 years BP. And the numbers here and the contours represent a reconstruction of the extent of the Laurentide ice sheet at different times before present. So 12 is 12,000 years BP and 9 is 9,000 years BP. So people have produced these reconstructions in an attempt to, model glacial isostatic adjustment and the uplift rates that you get when you move the ice sheet. And this is one estimate of GIA, glacial isostatic adjustment, over North America. And the black dots here are GPS stations over different parts of North America that are measuring uplift rates. And the interesting thing about GPS data is that there's multiple signals that in the VLM, the vertical land motion, that they observe. They're observing the viscous response due to GI, but they're also observing an elastic response to, for example, changes in land hydrology loading. So, you know, if you have groundwater reservoirs that are gaining or losing mass, that affects the signal as well. And then you've got tectonic effects and local subsidence superimposed on those observations. But what you can see here is that this is the Hudson Bay, this area here. The uplift rates are exceeding a centimetre a year. So they're quite big signals, up to about 13 millimetres a year over parts of North America. So that was just an aside. GIA is a fascinating problem, and it's something we're trying to tackle from a data-driven approach rather than a modelling approach in our global mass project. Back to sea level rise. This top graph here is a plot or a reconstruction of sea surface or sea levels during what's called the Common Era. It's actually over the last 2,500 years, and this was a very influential, important result when it was published in PNAS a few years ago. In fact, Barack Obama actually tweeted something about these results. And you know, he may not be your favorite president, but I think, you know, when the president of the US tweets your science results, that's quite kind of, it means you've landed, doesn't it? It means, you know, it is definitely catching attention of policymakers. And there's two reasons why this particular result really hit the headlines big time. The first is that so over the right here is roughly sea level in 2000. Actually, if we plotted it to 2020, it would be even higher, and the gradient will be even steeper. But what you can see is that in 2000, sea level was higher than it has ever been over the last 2,500 years. And I think possibly more importantly is that the gradient is steeper. In other words, the rate of change. So we're seeing an acceleration in sea level rise that's unprecedented in the Common Era. So that's pretty disturbing. And the bottom plot here shows a temperature, focus on the green line, it's temperature reconstruction for the same period. And not surprisingly, they're not in perfect, they're not perfectly synchronous, but you know, there's a quite a tight relationship between temperature changes and sea level. So that's what sea level has been doing in the past. And as I mentioned, if you look at the satellite altimetry data for the last 30 years, actually it's even more disturbing than that, because we from the satellite altimetry data, we've seen an acceleration or an increase in rates by about a factor 3 compared to the 20th century. So it's not 20%, it's not 30%, it's 3 times faster sea level rise in the last decade or so compared to the rest of the 20th century. What about projections? Well, so I don't know how many of you are familiar with all the jargon around different climate forcing scenarios, but this RCP 8.5 stands for Representative Concentration Pathway. It's a kind of projection of what the climate might do in the future. And 8.5 is a warm world. It's where it's close to what we call business as usual. That's where we carry on increasing greenhouse gas emissions forward in time. And RCP 2.6 is a kind of mitigation scenario where we attempt to reduce our emissions, and we stabilize at about 2 degrees by 2100. So this is the red one is kind of, worst case, and the blue one is probably actually best case, in fact, a bit optimistic. But just look at the numbers here. So B19 actually is from a study we published using something called structured expert judgment, which is a really interesting approach, which I haven't got time to talk about here, but just look at the range for the business as usual, the red scenario here. The range, the uncertainty, the spread, that's 1 sigma, 1 standard deviation, is actually larger than the signal. So in other words, that's by 2300, but even by 2100, we can see that, the range is, well, probably 1 sigma range is about a meter, and the signal is sort of around about, median value is about a meter. But actually that plot, so in other words, huge uncertainties in our projections of sea level rise in the future. But that plot is actually quite misleading because if you look at the median, which is the dark lines, and the bars are 1 sigma, it looks like it's kind of roughly Gaussian, but actually that's not true at all. This is from our PNAS paper in 2019. Don't worry too much about the details, but red here is equivalent to RCP 8.5 and blue is like our RCP 2.6, say. But the key thing about this PDF is it's definitely not Gaussian. It has a long fat tail, an upper tail. And so these numbers here, 22 and 112, they're 1 sigma, and that the ends of the bars are 2 standard deviations. So 95% confidence, or 90% credible range rather. So if you go to the 95th percentile value, it's 178 centimeters from ice alone. If you add glaciers and ice caps and thermal expansion, you exceed 2 meters. And so it's really important to understand the full distribution, not just, stick to, let's say, 1 standard deviation uncertainty. And these long fat tails are what in the jargon people call low probability, high impact events, which, are really important to capture in whatever approach you use to modeling the system. So I briefly mentioned, the various components to sea level rise. You've got vertical land motion, hydrology, ice, and you've got ocean processes. So those four different things going on. Accounting for each of those 4 components is called closing, or attempting to close, or solving the sea level budget. And that's what we're trying to do in the ERC project, Global Mass. And this slide just describes in words the approach we're taking, which is very different from, in inverted commas, the traditional approach that has been used for solving the sea level budget. Traditionally, geoscientists have kind of stuck in their various silos. So the oceanographers have done the ocean part, and the hydrologists have looked at their bit, and the glaciologists have done the ice bit, and the geodynamicists have looked at the solid earth bit, and they've added all those numbers together to get the total. So it's very much a kind of individual components, but there are various flaws and weaknesses in that approach, which we felt needs to be addressed. And so what we're trying to do is tackle all of those components simultaneously and consistently in the same framework. And we're using something called Bayesian hierarchical modeling to do that. And these are, so GMSL stands for global mean sea level. So that's the globally average change in sea level. And that is approximately equal to, steric is thermal expansion of the oceans. It also includes changes in salinity, but that's small. Change in mass of the oceans, that's due to mainly melting of glaciers and ice sheets, and VLM is your vertical land motion component. And those three terms are roughly equal to, or can be observed by Argo, is a network of ocean buoys that measures the first term. GRACE, I'll say, for those of you that are not familiar with GRACE, but it's a gravity mission, that in principle can measure ocean mass, and GPS in principle can measure vertical land motion. The problem is that GRACE and GPS are not measuring mass and VLM alone. They're superimposed on those observations are other processes. And so you have what's called a source separation problem. And the integral of these observations, or these three processes, is also observed by satellite altimetry, which measures changes in sea surface height. So you've got various different ways of looking at the sea level budget. And the kind of key aims of the Global Mass Project, which was, well, it's actually a 6-year project now, are these. I'll race through them. The first one was to produce a data-driven solution. Instead of trying to model GIA using a model of mantle properties and earth structure and ice loading history, which is very poorly known, as is deep mantle viscosity, we were going to produce an entirely data-driven solution. So not really relying on forward models at all. And it would be consistent with the observations and our understanding of the various processes. Actually, we didn't manage that. It proved a little bit too difficult to separate out the signals, the processes influencing the observations, our GPS data and GRACE data and so on. And so actually, in the end, we weren't really able to do that. But these other four we're still working on. So those of you not familiar with GRACE, it stands for the Gravity Recovery and Climate Experiment. We've got a reasonably long time series, sort of launched in 2003. The first two satellites lasted until 2017, but that original mission was replaced by something called GRACE Follow-On Mission, GFO, which was successfully launched and operated in 2018. So there's a little gap in data, but we have a pretty much continuous time series since, well, almost continuous since 2003. And just, is that going to play? GRACE, absolutely amazing technology and amazing data that comes from the mission. It's two satellites flying in tandem, separated by about a distance of 200 kilometers, with a microwave ranger between the two satellites. And as the first satellite flies over an area of, let's say, high density mass or a mountain range, something like that, and the gravity field is a bit stronger, the first satellite gets pulled towards that mass a little bit faster, so it accelerates. And the distance between the two satellites changes as you fly over different areas of the surface of the Earth. And the microwave ranger was able to measure differences in distance to a few microns, about the width of a human hair over 200 kilometers. And those tiny changes in distance between two satellites allows us to reconstruct the changing gravity field of the surface of the Earth over time. So really revolutionary data, I would say. This is an example of 7-year time series of changes in mass loading over the whole of the land surface. We're not looking at the ocean here, but these blue areas represent areas of mass loss. In other words, this is where we don't have ice. This is due to reductions in land hydrology. So we've got a drought over the Tibetan Plateau. We have enhanced monsoon conditions over the Indian subcontinent. We've got increased precipitation over the Amazon basin over that time period, and all sorts of other processes going on. Really amazing data. These blue areas, so this is the Gulf of Alaska. That blue represents mass loss from Alaskan glaciers, and also same in Greenland and along the Antarctic Peninsula here and so on. And what I mean, it really is beautiful data. This is just an example of GRACE data being able to observe the changes in lower mantle, mass movement in mantle after the 2004 Sumatra earthquake and the 2005 Neos earthquakes. So we can actually measure, the changes in not mantle density, but the relocation of mantle after those earthquakes. So that was a bit of an aside about GRACE. I'm going to have to speed up a bit here. Yeah, I'm definitely going to run out of time, I think. This slide just schematically shows the concept for how we were going to simultaneously solve for all these different processes that influence the sea level budget. And that's this middle layer here, what we call the process layer. There are 3 layers in a Bayesian hierarchical model. Yeah, let's start with the process layer in the middle. So these are the processes that we're interested in solving for. And there's 2 processes in the ocean: changes in ocean density, that's thermal expansion, and changes in ocean mass due to melting of glaciers and ice sheets, and land hydrology. We've got solid earth processes. I mentioned glacial isostatic adjustment taking place here that influences sea level, not very much globally, but locally at the coast, it can have quite a big effect. And we have 2 land processes, land surface hydrology and ice. And we want to solve for all 5 of these different processes. And we do that by combining a suite of different observations. So we've got some in situ data. Argo buoys measure density and temperature in the oceans, got altimetry of sea surface height, tide gauges, measure relative sea level, point observations. GRACE is a geopotential field. We've got GPS, we've got ISAT and cryosat that measures ice mass changes, and various other data sets. All of those are providing information about these different processes. But in addition to that, we have what's called a parameter layer. And this is, I think, one of the real strengths of, if you like, this kind of machine learning this sort of approach, that we can provide expert understanding and knowledge of the physical characteristics of the system to inform the solution. And that's really what the parameter layer. It's basically different types of prior. And so one example is, for example, we can impose conservation of mass. We have to say whatever leaves the land has to go into the ocean or the atmosphere. We can even conserve things like salt. So if we are melting fresh water on land, that's going to change the salinity of the oceans, and that has to be consistent. So all those sorts of constraints can be applied to improve the solution and help us with the source separation issue. But it's quite a challenging problem. If you take GRACE data, GRACE is influenced by all 3 of these, well, actually all 4 of these processes. Ocean mass, GIA affects GRACE because of changes in mantle structure. That affects the gravity field as well, and obviously land hydrology and ice. So all 4 of those are being observed by this single measurement. And that's true of almost all of those measurements, apart from the Argo data. They're all measuring multiple processes. So we have a sort of source separation challenge. Yeah, I'm absolutely going to have to speed up here. This is kind of the only real, if you like, detailed plot that I was going to show. And it's just to illustrate the approach that we're using here. I don't really have time to go into the details, but the green dots here are noisy observations of a rough process. The blue line represents a process with high frequency variability, and the red line represents a process that is smooth either in space or time. The x-axis here can be either time or space, it really doesn't matter. And the black line is a biased model estimate. So it's got some systematic bias, which is very difficult to actually identify or capture in models. And if we use our biased model estimate combined with the observations to reconstruct the blue observations, we get this black line here, which in itself is biased, obviously. So we get a biased estimate of our high frequency process. However, and remember, what's really important to remember here is that we only actually have one set of observations, but we have two processes we're interested in. But we know something about the roughness, or how smooth the process is in space and time. So we know that the red one is smooth and the blue one is rough. Just with that information about smoothness and these noisy green observations, we can get unbiased estimates of the blue process and the red process by using information about smoothness. And that's one of the key tools that we use in our source separation problem in the Bayesian hierarchical model. Right, so there are some really big, serious computational challenges. We're trying to invert a very large number of observations simultaneously. So we have to do some dimensional reduction. We can't use MCMC approaches because they scale roughly by the cube of the number of observations. So we have to use a sort of approximation to MCMC, which is called integrated nested Laplace approximation, or INLA, which is much more efficient when you have a large number of observations. I haven't really got time to go into the details, but in fact, in the end, one of the biggest problems that we're facing with the project in general is that each of our observations that I described earlier has sort of different measurement characteristics about them. Some are formal errors, some are really just the kind of random errors in the observations, and some are some combination of the two plus some estimate of systematic errors. And it's proved very, very difficult for us to account for the errors in a consistent way between the different observations that we have. And this is just a sort of snapshot of the time series of observations that we have that give us some information about changes in sea level over time. So we've got tide gauges, sea surface temperature, GPS, and so on and so on. And there is what we've called a Goldilocks period from about 11-year period where we have really good sampling of all the key observations that we're interested in. So initially, we're solving for that 11-year period. And this is just the kind of observations that we have. This is sea surface height. It's important to note that this is a mean of about sort of, well, 14 years, a little bit less, 12, 13 years of data. And you can see that there's a lot of variability in the mean change in sea level. And the rates there are between -10. So in other words, some parts of the ocean are actually going down over this 13-year period to +10 millimeters a year. This is the distribution of Argo buoys. There are sort of, I think, almost 5,000 over the global oceans now. Point observations, very different from, say, altimetry. These are our GPS stations, about 15,000 of them. Obviously, they're not independent observations. They're all, where they're clustered, they're observing the same process, so they are correlated, and we have to account for that. And we've got GRACE data, which is a geopotential field, but very coarse resolution. And we want to combine all those different observations with different spatial temporal sampling characteristics to solve for those processes. I'll skip that. And just because I want to give a little bit of time for questions, I'm going to very, very, very quickly show you some results for a proof of concept study just for the Antarctic ice sheet. Much easier problem, much smaller domain, and less process to solve for. So these are our observations over Antarctica that we were using. So we've got altimetry, which measures elevation change. We've got GRACE, which measures geopotential mass, and GPS data, which measures vertical land motion. And we combined those different data sets to solve for the details here don't matter, but this is the whole of the Antarctic ice sheet, and the y-axis here is changes in mass in gigatons a year over time. The red line shows ice dynamics, so you can see that that's a smooth process in time, and the blue line is what's called surface mass balance. That's basically changes in snowfall, and you can see that that's a relatively rough process in time. And so we could separate out these two processes, which are controlled by very different well, climate forcing and physical mechanisms. So it's quite important to understand what processes are taking place. And this just illustrates the fact that we can, it's not just resolving changes in time, but we get a lot of spatial detail about the various processes that we're interested in solving for. On the left here, we have a plot, our reconstruction of changes in snowfall, and on the right is the results from a regional climate model. And you can see that there's relatively good agreement, but actually we have greater confidence in our inverse solution than we do in the regional climate model. So we can actually use it as a kind of validation. So that was really a kind of whistle-stop tour over some of the sort of problems I've been working on. We're developing the Bayesian hierarchical model further, and we're hoping to actually generalize it so we can tackle a whole class of different problems, not just in geosciences, but in any kind of 4D problem that you might be interested in. And I will stop there.
Aya, you're muted.
Sorry. Thank you again for the nice and interesting talk, Jonathan. And now the floor is open for questions from the audience.
Yeah, sorry, I did sort of run over a little bit. I thought that might happen actually, but
It's actually a later start, so no worries.
So I see some hands rising. So maybe Jürgen Kusche first, and then Xiaoshang next.
Thank you, Jonathan. This is a great talk, and these are really interesting results. My question would be regarding the last part. So you compare the climate modeling for Antarctica, the surface mass balance, and the inverse solution.
yeah,
And you said you have more trust in the inverse solution.
Yeah.
So what is not covered by the climate modeling are things like the warm water underneath the ice tongues. We know that there's temperature rise in the region, in the ocean water where we have the grounding zone, things that are happening, so to say, underneath the surface. And I wonder, and of course, there's also very few observations, like from
right.
Submarine UAVs and buoys and so on. Is that something that you could solve for? I mean, if you trust the inverse solution, and I mean,
Well, it very much depends whether your observations are informative about subsurface processes or not. Because obviously, you know, with satellite, with Earth observation, you're really just measuring, well, unless it's something like, it's gone, but, you know, unless it's like a very long, you know, L-band radiometer or something, you're generally just measuring surface processes. And so it would be some kind of indirect, you have to indirectly infer something about subsurface processes from that, which is possible. You could use, for example, conservation of mass. So, you know, you could, we know the direction of flow, so you can do flux divergence calculation. And that gives you information about bottom melt, for example. I mean, people have done that, combining SAR interferometry with estimates of surface snowfall. So you know how much is going in and where it's going. And you know, again, conservation of mass means you know, it can't disappear. So if it gets thinner, for example, then that must be due to bottom melt. Well, I just went back to this slide though, just to sort of emphasize, I didn't have time to talk about this, but these bottom plots show our estimates of the change in surface mass balance for different basins, and the red dots are from the regional climate model. And just the only thing I want to say about red dots is there's no uncertainty, they're just dots, because what is the uncertainty on a climate model? It's almost impossible to actually derive. People use, you know, ensemble estimates, but that just gives you some estimate of, I don't know, you know, internal consistency or you know, the parametric uncertainty. It's not a genuine estimate of, you know, how confident you are in those values. And that's a big problem in climate modeling.
Thank you. Mm-hmm.
Okay, then Xiaoshang, please.
So thanks, Jonathan, for this eye-opening talk for somebody who is not expert in earth sciences. Yeah, so your last statement, it's impossible to quantify uncertainties. This sounds a little bit pessimistic.
Well, impossible, perhaps that's a bit extreme, very difficult, let's say very, very, very difficult.
Yeah. Okay. So exactly in this direction. So looking forward, now there is a big trend to combine machine learning models with the physical models, and also towards quantification of possible uncertainty. So what is your, let's say, perspective on this? So where we can...
So machine learning is great, okay, but it's only as good as the input you give it. In other words, the training data. And the challenge with sea level rise, and in particular what the ice sheets are going to do, and that's the big question about prediction, is that our observational record is not long enough to capture the full parameter space, the full, you know, potential variation of the system. And so I mean, and that's a problem with many of the probabilistic approaches that have been used for projections. You can only, so the probabilistic approaches are very similar. They're trained on, you know, observations, or informed by observations, let's say, actually. But, you know, if you don't have an observation of, let's say, the marine ice sheet instability actually ever happening, you can't train it. Your machine learning algorithm will never know it exists. And, you know, there's a really nice, I work with a bunch of statisticians, and one of them is an economist, and he gives the example of, you know, the stock market crash in 2008, and you know why none of the economic models were able to forecast that? Because they were using something called a Gaussian copula. You know, copula describes the interaction of two variables for different conditional probabilities, and like they just weren't able to reproduce that inflection point, that kind of, if you like, change point that happened in 2008. Exactly the same problem with parts of the climate system that are not well observed. I don't know, does that kind of answer This is sort of, again, is that too pessimistic?
Yeah, we have, let's say, 3 years time to discuss together where we can improve, basically.
I think
we have
Jürgen put his hand up again, actually, but I
yes,
don't know.
Jürgen, Jürgen, we have a couple of minutes. I mean, we started 10 minutes late, so I think we have 5 more minutes for further question.
Thanks.
Maybe a question for both of you, Jonathan and Chatsu. Maybe something for the next 3 years. So I know that the inverse approaches, I mean, there are many ways how to set up an inverse approach, and we did try to do something also in Bonn. So what I always wonder is whether it's possible to use machine learning methods basically to design your inverse approach to, let's say, to learn the best structure of an inversion approach. Which are the parameters that you need to resolve for, what people otherwise do in sensitivity studies, for instance?
I think absolutely. And I think that that's where ML approaches will have some real wins or real benefits. And there are parts of, you know, a GCM, a general circulation model, is millions of lines of code. There are hundreds, perhaps, I don't know, yeah, let's say hundreds of tunable parameters in those GCMs. And some of them actually are very well informed by observations. And I think, you know, for that part of the climate system or climate model, ML approaches have real value and real potential, and actually can replace sort of rather unsatisfactory parameterizations. But you know, it's like any kind of model. Any model of any system, you have to make sure it's fit for purpose. So you have to make sure you're getting the model to ask the right questions that the model is fit to ask. That the risk is that you make your model ask questions that it's unfit for, that it doesn't have the skill to address. And I think that that's the balance you have to get with ML approaches. That there are some things, and it goes back to my point about training data. You know, I think with ML, training data is everything, isn't it, really?
Yeah, so since the question is addressed to both of us, I would also add my 2 cents on that, right? So for all these kind of machine learning for inverse problems, to have an appropriate sampling the parameter space to train a proper model is of course necessary in order to more or less mimic the process. Actually, this is also a perfect time for me to advertise the next lab talk, which will be given by Yuan Yuan on machine learning for inverse problems. So maybe this could be interesting for you also, Jürgen.
Thank you, Zhaojiang.
Great. So I think one last question from Sol. We can
Great,
still address.
thank you. Talking about the data sets and making predictions, I was curious how these models are validated, because I know you talked about like the stock crash and economics or economists not being able to predict that because it wasn't in like training data. I was wondering how you partition the observations that you receive into like a training and into a validation set.
Well, there's no one answer to that. I mean, because it entirely depends on what part of the climate system you're interested in or what problem you're trying to address. And it goes back to my question, you know, so there is, it's not done very much, actually. It should be done a lot more, but with models, you can do a calibration exercise, like a Bayesian calibration, where you say, well, you know, you give it a skill score, you think it, but you have to, you can't do that for every part of the climate system. You have to say, so let's say I'm interested in, I don't know, Arctic temperatures. Well, then I have to use observations from the Arctic as some kind of you know, target. And I don't think there's kind of any one. It's slightly different actually. So the GCMs, the general circulation models that you see, they haven't used, for example, a 20th century temperature record as a training data set. They use it as a target. So if they reproduce it, they say their model is working well. Mm-hmm. But that's not entirely true. That's a kind of sleight of hand, we say. It's almost dishonest, because actually, if their model doesn't reproduce 20th century temperature record, they throw it away, or they start tinkering with, you know, these tunable parameters until it sort of kind of does. So mm-hmm. You have to be very careful. There is often a lot of circularity in how any numerical model of environmental system has been tuned, and they're all tunable. And it's a big, it's a big issue I have with deterministic modeling, actually.
That makes sense. Thank you.
But I should say that actually I've met Sol in person, which was very exciting yesterday. So one of the few so far.
Okay, great. So thanks again, Jonathan. And yes, I think there's still plenty of room for further discussion and collaboration.
Great. Okay.